12 customers got confirmation emails for the same seat during a flash sale. The team assumed the database transaction was atomic, but the seat inventory update used select for update without a proper index, causing a table lock. When the lock wait exceeded the 5-second timeout, the booking was created without the seat update because the transaction was split across two services via HTTP. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design a flight booking system. A flight booking system is a distributed transaction orchestrator that manages seat inventory, payment processing, and booking confirmations across multiple services while ensuring no double booking occurs and payments are idempotent. Most tutorials show select for update, but that becomes a bottleneck under load. If you hold the lock while calling a payment gateway, you'll exhaust your database connection pool. The fix: optimistic locking with a version column. Here's the optimistic locking code. It updates the seat only if the version matches. If 0 rows are affected, the seat was already booked or version changed, so you retry. Idempotency keys are your shield against duplicate payments. When a payment request times out and the client retries, the key ensures the gateway doesn't charge twice. Here's the idempotency check. If the key already exists, return the existing booking without charging again. Otherwise, process payment and create the booking. A booking involves multiple steps. If one fails, you need compensating actions. The Saga pattern orchestrates steps and runs compensations in reverse order on failure. This Saga orchestrator executes steps in order. On failure, it runs compensating actions for completed steps. The state is persisted for recovery. When you update inventory and create a booking, you often need to publish an event. If the queue publish fails after DB commit, you lose the event. The Transactional Outbox pattern solves this by writing the event to an outbox table in the same transaction. Here, the booking and outbox event are saved atomically. A scheduled job pulls unpublished events and publishes them. If the queue is down, it retries on the next pull. To avoid holding locks during payment, use a reservation with a TTL. Reserve the seat with a timestamp, process payment asynchronously, and confirm only if within TTL. Expired reservations are released by a background job. This code reserves a seat for a TTL, confirms only within the TTL, and releases expired reservations every minute. This is the same issue we highlighted at the start. Here's exactly why that happened. The seat inventory update used select for update without a proper index, causing a table lock that serialized all writes. The booking service had a 5's timeout, and when the lock wait exceeded that, the booking was created without the seat update because the transaction was split across two services via HTTP. The fix was to move seat inventory and booking creation into a single service with a local transaction. They added a version column on the seats table and used optimistic locking with retry. They also set a 30's timeout on the inventory lock to prevent long waits. Never hold a database lock while waiting for a payment gateway. This will exhaust your connection pool under load. Use optimistic locking or a reservation with TTL instead. The update where it equals and version equals. Syntax is standard SQL and works in PostgreSQL, MySQL, and most databases. However, MySQL requires set version equals version +1 to be placed before the where clause in some contexts. Always test your specific database version. The article mentions storing idempotency keys, but does not show the database schema. Use a unique constraint on the idempotency key column to enforce idempotency at the database level, preventing duplicate booking records even if application logic fails. When using TTL-based seat reservations, ensure the background job that releases expired reservations runs frequently enough, e.g., every minute, and handles clock skew between application servers. Use a database timestamp, e.g., now, rather than application-generated timestamps to avoid inconsistencies. Here are the debug commands to diagnose issues. Check for duplicate bookings, payments without bookings, and long-running locks. Use these to quickly identify the root cause. Let's run through some common interview questions. How does optimistic locking handle concurrent seat bookings? Both red version equals 1, first update succeeds, second retries with new version. When to use Saga versus 2PC? Saga for distributed services and high availability, 2PC for strict atomicity with lower throughput. How to prevent double charging on network failure? Use Idempotency key. Gateway returns same response on retry. And a few frequently asked questions. How to prevent two users booking the same seat? Use optimistic locking with version column. What's the difference between optimistic and pessimistic locking? Optimistic checks version at update. Pessimistic locks row until transaction ends. How to handle payment failure after seat reservation? Use Saga with compensating action to release seat. To summarize, use optimistic locking with version columns. Always implement idempotency keys on payments. Use Saga pattern for distributed transactions. Employ Transactional Outbox for reliable events. And use TTL-based reservations to avoid holding locks during payment. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.